Hot Wheels cars were dropped down a parabolic track. The maximum velocity at the middle of the track was measured using data studios, and the final height was measured using a meter stick. Calculations were done to determine the coefficient of friction of the track. The coefficient of friction was multiplied by 2 to predict the friction of a loop. Modifications were done to the track and the car to determine the maximum speed the Hot Wheel car could reach. Using the maximum velocity and the coefficient of friction, the maximum radius of a loop was determined. A track with the maximum height loop was constructed and tested. The objective to send a Hot Wheels car through the largest possible loop was met.
Kinetic energy, energy of motion, energy of the car moving down the track. Potential energy, the energy due to the position of the car. Mechanical, the sum of the potential and kinetic energy. Conservative force, the work must be path independent. The work done by a closed path must be 0. If the force does not meet the criteria, it is a non-conservative force. Example, friction. The car experiences friction when moving down the track. A uniform circular motion. An object moves at constant speed in a circular path. Centripetal acceleration, always directed towards the center of the circle. For example, when the car goes around the loop, it experiences this.
There were 3 parts of the lab. In part 1, the main focus was non-conservative forces. The ends of a Hot Wheels track were taped to each end of a table, and the middle of the track was taped to the floor next to the photo gate. The distance from the end of the track to the middle of the track was measured and recorded. Then a piece of tape was added to the car, and the mass was recorded.
Yep.
In part 2, the main focus was maximizing velocity. 3 controlled run trials were experimented. These trials were all ran at the same height of the track at an incline. The velocity was recorded using the motion sensor, and the gravitational potential energy and the kinetic energy were calculated using the equations provided. This led to findings the change in the energy. Next, modified runs were conducted. In the first trial, the height was adjusted to a higher incline. In the second trial, a slingshot was made using a rubber band. In the third trial, a bigger slingshot was made using multiple rubber bands. In the fourth trial, the big slingshot was continued, as well as lubing the wheels of the car. In trial 5, a bigger slingshot was made, as well as lubing the wheels. In the 6th and final trial, the biggest slingshot yet was made, and the wheels of the car and the track were lubed. The velocity was recorded by the motion sensor for each different trial, and as each modification was made, it got progressively faster. Using the calculated gravitational potential energy and kinetic energy, the change in energy was calculated for each trial by the equations given. After this section of the lab, we were able to find the potential radius a car could travel in a full loop for the next part of the lab. Based on the previous stages and calculations, we determined a loop size that our car could pass through. The radius of the loop we used was 1.025 meters. Multiple trials were done using the earlier modifications until the car successfully completed a full loop.
Yep.
The objective of Part 1 was to find the coefficient of friction of the track. Using the potential energy, kinetic energy, and work equations, we were able to calculate the coefficient of friction from 3 different trials. The average coefficient of friction was taken and came out to be 0.167. which was then multiplied by 2 to give us a coefficient of friction of 0.334. The objective of part 2 was to maximize the velocity of the car. 3 controlled runs were done to give us an average change in energy of negative 0.24. Then modifications were done to the car, such as adjusting the height, making a slingshot, and lubing the track and wheels. These modifications gave us a velocity range of 6.33 meters per second to 11.36 meters per second. Using the equations on the chalkboard, we calculated the maximum radius using the velocity, gravity, and coefficient of friction. Our maximum radius could be 1.85 meters. The objective of part 3 was to test the car on a Hot Wheels loop. Using the modifications to maximize velocity, our car was able to complete a loop with a radius of 1.025 meters.
The objective of the experiment was to successfully send a Hot Wheels car through a full loop. The objective was met as the car made it through a loop with the radius of 1.025 meters. By determining the coefficient of friction and maximizing velocity, we were able to predict the radius that our car could complete. Any error in this experiment could be from human error, such as imprecise measuring. One way to further this experiment is to do more modifications to try to increase velocity, which in turn would increase the possible radius of the loop.